Hey everyone, so in this video we're going to be talking about confidence intervals, and this is going to be the first video in a series of videos about confidence intervals. But first let's talk about what's called point estimation. So remember, we typically don't know what the value of population parameters are, such as mu, sigma squared, or p, the population mean, the population variance, or the population proportion. And usually what we do is we try to estimate those using statistics from a sample. And these usually provide good estimates for the population parameters. So for example, we'll use the sample mean to provide an estimate for the population mean, or we could use the sample proportion to provide an estimate for the population proportion. And these estimates are called point estimators. And the estimators that we consider to be good estimators are the ones that are what we call unbiased. And I have good in quotes here because there are multiple ways to define a good estimator, but usually the ones that are used in practice are the ones that are what we call unbiased. So for example, the sample mean X bar is an unbiased estimate for the population mean mu, and the sample variance S squared is an unbiased estimate for the population variance sigma squared. Now remember, in the sample variance, it looked kind of funny because we were dividing by n minus 1. And the reason we do that is because it provides an unbiased estimate of the population variance. And that whole topic is way beyond the scope of this video, but that's why we use it. So now let's talk about interval estimation. So we actually don't really care that much about point estimators because they fail to take uncertainty into account. So for example, if we estimate the average age of NIU students is 21.4 years with a sample of size 10, how confident would we feel about it? On the other hand, what if we estimate that the average age of NIU students is 21.4 years with a sample size of 200? Now, how confident do we feel about it? And we could even make it more extreme. Let's say we talk to one student who is 21 years old. How confident do we feel about saying, oh, the average age of all NIU students is 21 years old? Not very confident. But if we talk to 400 or 500 NIU students, and we found that the average age is 21 years old. Now we're feeling pretty good about it because we have a lot of evidence to back up our claim. So using intervals to estimate a population parameter allows us to quantify the amount of uncertainty we have with our predictions. So this is where confidence intervals come in. So a confidence interval is an interval around a point estimate that provides an estimate for a population parameter with a specified level of confidence. So from the previous example, we estimated that the average age of NIU students is 21.4. So now with confidence intervals, we could say something like, we are 95% confident that the true mean age of all NIU students is between 20.2 years and 22.6 years. And we're going to go over how to calculate this interval. So suppose we have a population mean mu that's unknown, and we have a population standard deviation sigma that is known. And then our confidence interval is going to be this. This is going to be X bar plus or minus Z alpha half times sigma over the square root of n. And we'll go over what a lot of this means in just a moment. What this does is it's going to provide us a 100 times 1 minus alpha percent confidence interval for the population mean mu. So let's take this piece by piece here. So Z alpha half, this piece right here, this is what's known as the critical value, and we'll go over what that means in a minute. Sigma over the square root of n, which is this piece right here, That's known as the standard error. And that should look pretty familiar to you because this is actually the same as the standard deviation of the sample mean, x bar. And then this whole piece, z alpha half times sigma over the square root of n, this piece right here, this combined piece is known as the margin of error. So let's talk about each of these pieces one by one. Z alpha half is known as the critical value. And what we mean by alpha here is alpha could be thought of the area outside of the confidence interval. So it's the opposite of our confidence level. So for example, when we have a 90% confidence level, our alpha is going to be 0.10. Similarly, when we have a confidence level of 95%, our alpha is going to be 0.05, and so on. So the area outside of the confidence interval is going to be split up into two equally sized tails since we're splitting alpha in half. So that's where the alpha half comes from. And we'll see an image of this in just a second. So as promised, here is that image. So this is x bar. This is going to be the center of our sampling distribution. And what we're doing with this confidence interval is we're providing a lower bound for what we think the population mean is, and we're providing an upper bound for what we think the population mean is. So that's where the plus or minus comes from. We need a lower end that we're subtracting from x bar, and we need an upper end that we're adding to x bar. Now, this is where the margin of error comes from, because here we're taking x bar and subtracting something from it, and that something that we're subtracting is the margin of error, as we talked about earlier. And the same thing on this other side. We have x bar and we're adding something to it, and that something is the margin of error. Now, when we were talking about alpha, remember the area outside of this confidence interval, the area outside of this yellow area right here, that's going to be alpha. So that's going to be this white tail right here and this white tail right here. And remember, since there are two of them, we have to split alpha in half. So half of alpha is going to be here, and the other half of alpha is going to be here. So if alpha is 0.05, we'll have 0.025 here and 0.025 here. So what's left is going to be 0.95. So what that tells us is that this yellow area right here is going to be the middle 95% of this distribution. And that's how we construct our 95% confidence interval. So let's look at an example. So suppose the average amount of gas purchased on a given day from 49 customers at a gas station is 9.2 gallons with a known population standard deviation of 3.1 gallons. And let's say we're asked to find a 95% confidence interval for mu. And in this case, mu is going to be the true mean number of gallons purchased at that gas station. So, first of all, I always recommend listing out all the information that's been given to us already. So, here we have the average amount of gas purchased on a given day from 49 customers, and that average was 9.2 gallons. But that's from just the sample of 49 customers. So, this is going to be our sample mean here. So, our sample mean was 9.2. And this was from 49 customers, so N is going to be 49. And then we know what the standard deviation is. This is the population standard deviation, so we get to use sigma here. And this was 3.1. And remember, our formula was x bar plus or minus z alpha half times sigma over the square root of n. And we actually have all of these except for z alpha half. So let's go ahead and drop them into the formula. So x bar was 9.2, so that goes right here. And then sigma was 3.1, so that's where this goes. And then n was 49, so this goes right here. So again, the only thing that we're missing here is z alpha half. So let's figure that one out. So we're looking for a 95% confidence interval. So since our confidence level is 95%, what's left is 5%. So we can say alpha is 0.05. And remember, since we're splitting this up into two tails, we have to divide alpha in half. And what that's going to give us for alpha half is 0.025. So our z alpha half is z 0.025. And what this critical value is going to be is the value of z that contains an area of 0.025 in the right tail. So what we'll see down here is that z 0.025 is right here because the area in this right tail, this yellow area, is 0.025. And this concept may sound familiar to you because this is the same thing we were talking about when we were talking about percentiles. If there's 2.5% above this value, that means 97.5% is below this value. So that means z 0.025 is the 97.5th percentile of the standard normal distribution. And we know how to find that. So we could find this percentile, this 97.5th percentile on the z table. And when we do that, we'll find this in the middle of the table, and we'll find that the z value that corresponds to that is 1.96. So this critical value here is going to be 1.96, and now we can put it into the formula. So before we actually put it into the formula, there's actually a much easier way to find z alpha half. We can look on the bottom of the z table where the special critical values are listed, and you'll actually find this on most z tables that you see. So remember that we're looking for z 0.025. So if we look for 0.025 on this table right here, we're going to find that that value is 1.96. So that's what we're going to use for our critical value. And one thing to note here is that when we're working with z, 1.96 is always going to be the critical value for a 95% confidence interval. And that's really nice because anytime you're asked to calculate a 95% confidence interval and you're going to be working with z, you know immediately that 1.96 is going to be the z alpha half, the critical value. So now we can plug this into the formula. So remember we had x bar was equal to 9.2. We had z alpha half we just determined was 1.96. Sigma was 0.31. And the square root of n was the square root of 49. And then what that's going to give us is 9.2 plus or minus 0.868. And this 0.868, remember, is called the margin of error. And what this is going to give us is this interval right here. And the way we interpret that is we are 95% confident that the true mean amount of gallons purchased at the gas station is between 8.332 gallons and 10.068 gallons. So going back to this idea that z alpha half is going to be 1.96 anytime we're calculating a 95% confidence interval, there are actually some other key numbers that are worth noting because these are some very common confidence intervals that are calculated. Typically, in practice, you'll see 95% confidence intervals, but I have seen a few sprinkled in here and there that are for example, 90% or 99%. And these are the corresponding critical values that line up with those confidence levels. So with 95%, we used 1.96. If we were calculating a 99% confidence interval, we'd be using 2.58 for our critical value of Z alpha half. And like I said, 95% is by far the most common confidence level used in practice. So now let's go back to the age example. So from a random sample of 100 NIU students, the mean age was found to be 21.4 years. The population standard deviation is known, and it's 2.6 years. So now we're being asked to construct a 90% confidence interval for the true mean age of NIU students. So again, let's list out the information that's given to us. We have X bar, that's 21.4. We have the known population standard deviation, which is 2.6. And we have N, which is 100. And since we're looking for a 90% confidence interval, that means 10% is not in the interval. So that's where we get alpha equal to 0.10. And when we divide that in half, we'll get 0.05. So Z alpha half is going to be Z 0.05, and we can look that up on the table. So if we were to look that up on the table, we would find that for a 90% confidence interval, when we're working with Z, our Z alpha half is going to be 1.645. So that's what we're going to use. So when we plug everything into the formula, we'll get 21.4 plus or minus 1.645, which was our critical value, times 2.6 over the square root of 100. And that's going to give us 21.4 plus or minus 0.428. And that gives us this interval right here. And again, the way we interpret that is we are 90% confident that the true mean age of NIU students is between 20.972 and 21.828 years. So sometimes we're interested in keeping the margin of error lower than a certain number while maintaining a certain level of confidence. And the only way to increase confidence and make the confidence interval smaller at the same time is to increase the sample size. And this should make sense because as we gather more evidence, our estimates for our population parameter are going to be better and better. But the only problem is that increasing the sample size means gathering more data, which in the real world can often be pretty costly. So we'd like to gather as little as possible while still maintaining a certain margin of error. So the way we calculate a minimum sample size required for a 100 times 1 minus alpha percent confidence interval for the population mean mu, when sigma, the population standard deviation, is known, is the following. So this is going to be sigma times Z alpha half over B, all of that squared, and that's going to give us the minimum sample size required for a certain confidence level. Now, this is just a rearranged version of the confidence interval formula with n being isolated by itself. And B here is going to be the margin of error, and we'll go over an example of this. But remember, when we constructed confidence intervals, we were assuming that the distribution of x bar was at least approximately normal. So for the sample size needed calculation to be valid, either the population must be normal or the sample size must be greater than or equal to 30, or both. And then we're allowed to declare that x bar is going to be at least approximately normal, and then we can carry on with this calculation. And then one thing here is that we're going to always, always, always round up when we're calculating the sample size needed. So remember from the gas station example, we had a sample mean of 9.2, we had a population standard deviation of 3.1, and we were looking for 95% confidence, which gave us a critical value of 1.96. So what if we were asked how big of a sample size would we need if we want to be 95% confident that X bar is within zero point 0.5 gallons of mu? And the within zero point 0.5 gallons of mu part tells us that our margin of error is going to be zero point 0.5, and that's what B is going to be. So our sample size needed is going to be 3.1, which is sigma, times 1.96, which was the critical value, divided by zero point 0.5, which was the margin of error, all of that squared, and what we're going to get is 20.253 squared, which is 410.184. And even though we would normally round this down to 410, we have to round this up. And the reason why is because if we were to round this down and say, oh, well, 410 is going to be enough of a sample size, that's less than this. So that tells us that we didn't gather the sample size necessary for it to be enough. So we always have to overestimate the sample size needed to come up with an appropriate number. So we're going to round this up to 411. So we would need a sample size of 411 to be 95% confident that X bar is within zero point 0.5 gallons of mu. And again, if we had rounded down to 410, then we wouldn't have enough. We'd fall short of this sample size that's required. So we always have to round up. So anyway, that's the end of this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.